So in this video, you're going to look at another type of locus that you'll need for your exam. This is z minus u modulus is equal to z minus v. Here z is the complex variable whose locus we are trying to represent, and u and v are fixed points. So z minus u modulus, so let's say u is over here. This is u. It's like I'm representing it like a position vector, and let's say this is v. This is v. Now z minus u represents, z is a variable, so this represents the distance from z and u. Z minus v represents the distance from z and v. So this equation actually what it is saying is that z is a locus of points, z represents a locus of points such that its distance from u and v is the same. That is, it is equidistant from 2 points. So what we learned this in maths D actually. So this is, so z basically is the perpendicular bisector of the line connecting u and v. Z is the perpendicular bisector of the line connecting u and v. So this will be, z will be something of this nature. This will be z. Okay. So at the same, let's look at a specific example. Let's say so what will be the locus of z? 1, 2, let's say this is this point, then 2 minus 3, like somewhere over here. So z will basically be the perpendicular bisector of these 2 points. This is 1, 2, this is 2 minus 3. So z will be the z will represent the perpendicular bisector of this and this point. Let's say like this. Okay. Very simple actually. But now the question comes, how actually we get that. So one way actually I already showed, because this shows that z is equidistant from u and v. But there is another way that we can derive this. So let's look at this equation. Z is x plus iy. Z is a complex variable, x plus iy. So if I write this over here and simplify, I'll get this. Okay, I think from here to here you can get from here to here very easily. Now if I simplify this further, ultimately this is like x square, y square, they get cancelled. So ultimately this is the equation that I get. 10y minus 2x plus 8 is equal to 0. This are very similar equation, maybe in a different form. So we can actually verify that this equation is the perpendicular bisector, equation of the perpendicular bisector of the 2 points 1, 2 and 2 minus 3. We can find the equation of the perpendicular bisector of these 2 points and actually see that this and that equation will be the same. Or there is another way also that we can verify. That is, if you find the midpoint of these 2 points, let's say the midpoint is going to be 1.5 comma minus 0.5, and the gradient of the perpendicular bisector actually, okay, gradient of these 2 points is going to be what? Is going to be minus 5. Okay, so if the equation of this, the midpoint of this is 1.5 minus 0.5, So if this x value and y value, if we insert into this equation, it will be satisfied. That is one point. At the same time, what is the gradient? What is the gradient of this line? It's going to be 1 by 5, and this is the equation of these two lines. So perpendicular line, the gradient is going to be the, if two lines are perpendicular, the gradient is the negative reciprocal. So the perpendicular line, the gradient will be 1 by 5. Okay, so basically the midpoint passes through this equation, and the gradient of the perpendicular bisector of these 2 points and of this equation, the gradient of this equation is the same. So that in that way also you can actually, it's a way of showing that this equation is indeed the perpendicular bisector of the equation of the perpendicular bisector of the line joining 1, 2 and 2, -3.